Hi, my name is Terry Scully. I'm a systems engineer of the Battery Gauge Group, and today I'm going to talk a little bit about gauging considerations for industrial battery packs. So I'm going to talk about leveraging some of the features that we have in our gauges specifically for industrial applications, things like scaling for higher than typical voltage, current, and capacity, looking at reducing power dissipation in heavily duty cycled loads, talking about how to extend your battery pack life using some of our specialized charging algorithms, and then our EOS determination algorithm for rarely discharged systems. And then some of the gauges that we've got specifically for high cell count systems, including the BQ78350R1, BQ34Z100G1, and the BQ34110. We'll begin with looking at some of the features we have in the gauges and how to leverage those for industrial battery packs. So most TI gauges will natively support currents up to 32 amps, but we have a lot of customers that want to use much higher current levels than that. And so for that, you can use current scaling. For example, if you have a maximum discharge current of 48 amps, then based on our maximum of 32 amps, you'd need to scale the pack by at least a factor of 1.5. And so we round that up to about 2 times. And then you basically fool the gauge by, when you're doing the current calibration, for example, if you're using a 5 milliohm sense resistor, we can calibrate it, if you're actually using a current of 4 amps, you actually tell the gauge that you're really using a current of 2 amps during your calibration. And so then when it calculates the CC gain and CC delta, they calculate out thinking that you were using a sense resistor of 10 milliohms. And so then you have a calibration ratio of 50%. In order to do this, you do need to modify all the current and the capacity related data flash values by the scale factor that you're using. That includes the first level overcurrent thresholds have to go down, from 6 amps down to 3 amps, and a lot of settings like sleep current, quick current, design capacity, and design energy. There are a few exceptions which are related to the hardware protections in there. Those you want to leave based on settings that are like true RSense times your true current for the protection level that you're trying to implement. And then, of course, the gauge will be reporting the scaled current values. And so then in your host system, you have to take those values and then scale them up to actually get the true values that are being implemented. So we can also implement voltage scaling for systems where customers need to support much higher level voltages than the gauges can natively support. For example, our BQ34Z100G1 and BQ34110 can natively support pack voltage up to 65 volts. But for higher voltages than that, we can also modify the voltage divider that is used in the system, and then together with some modifications to the flash values, we can actually then support these higher level voltages. For example, in these systems, we need to have a voltage divider here such that we reduce the voltage that is being measured at the bat pin down to less than 1 volt. And so the divider has to be able to take whatever your maximum voltage is and divide down to that level. For example, if we have an 18S system, then if maximum pack voltage will be somewhere around 4.5-ish to 5 volts times 18, so 90 volts is kind of an upper level maximum. So if we want to take 90 volts and then divide that down to less than 1 volt, let's say 0.9 volts, we can calculate that out to see what resistive dividers that we need, what resistors we need in that. Generally, we try to keep this lower leg equal to somewhere in the range of 15 to 25 k ohms. We don't want it too high because then the transient for turn on and turn off gets kind of slow, and then if it's too low, you're burning kind of excess current that's not really necessary. So in this case, if we assume 16.5 k ohms with 90 volts here, to get 0.9 volts out, we need about 1.6 mega ohms for the series resistor up here. And so then taking a standard sized 1.62 mega ohm gives us about an 89 volt maximum pack voltage that we can sustain. So that works well for this system. In voltage scaling, you also have to modify some of the flash parameters. So we have to make sure that when the gauge is calculating the voltages, it doesn't calculate a reported voltage greater than the supported 65.5 volts. So in order to do that, what we do is we modify the value stored in the number of series cells. So for in this case, say we had the 90 volts, maximum versus our reported value can't be more than 65. That's a value of 1.38. And so then we can say, okay, let's round that up to an integer. So let's use a 2x scaling factor. So then what we would do in the gauge is we change, rather than telling it we have an 18S system, we would tell it we only have a 9S system. And then at the same time, while we're doing calibration, we do need to divide the voltage by the scale factor while we're calibrating. So if we're applying an 80 volt level to the gauge while we're calibrating it, then we'll actually only enter 40 volts into BQ Studio. And so then the gauge will calculate the corresponding level to that. And then, of course, the gauge will be reporting a voltage back that will be scaled down versus the true voltage. And so in the host processor, you have to take the reported voltage and then scale that up again to actually get true pack voltage. And note also, there is some limitations in that if you use this scheme, you really can't divide the number of series cells by a fraction, so you can't tell if you had a 17S pack, you can't go in and tell the gauge, oh, we only have 8.5 cells now. So there are ways to work around that, but in general, if you're using a even number of cells, then it's fairly easy to find some scale factors that will work for you. And capacity scaling is the other area where we run into customers who have much larger packs than what we may be able to handle natively in the firmware. Most of our gauges can handle up to about 29 amp hour for these multi-cell gauges, but we have many customers using much larger size packs than that. So for example, if you had an 80 amp hour pack and we can only support 29 amp hours, then you need a scale factor somewhere in excess of 2.75, so maybe 3x or 4x. And this approach is it's basically the same thing as we used for current scaling earlier. You basically will scale the current during calibration. So for example, if we're using a 5 milliohm sense resistor and we're calibrating with an actual current of 20 amps, we instead tell the software that we're only using 5 amps. And so then when it calculates the calibration values, it effectively thinks that you're using a 20 milliohm sense resistor. And so then we're ending up with a calibration ratio of 25% for a 4x scale factor. And then at the same as we were doing with the current capacity scaling, we have to modify various data flash values by that scale factor. First level overcurrent thresholds changing, sleep current, quick current, design capacity, and design energy levels. And again, just like before, there are some exceptions for the hardware protections. Need to stay based on true RSense times the true current level that you're wanting to set the protection at. And of course, you also have to still scale up the currents and the capacity values that you read from the gauge to get the actual true values. So next I want to talk about how you can use some of the techniques we've got in the gauge to reduce the power dissipation for heavily duty cycled loads. We run into a lot of customers with applications where they have a very low idle current for long periods of time, and then they have bursts of activity at high current during very brief windows. And so they're always looking for how can they actually reduce the gauge power during those idle periods in order to optimize their overall system lifetime. For example, say you've got a system that's configured where its idle current is drawing 100 microamps continuously, including the gauge all the time, and then you have these active bursts that are, say, 1 amp for 1 second per day, and your system battery is about 3,000 milliamp hours. So if you go through the calculations, the charge you're consuming per day while idle is on the order of about 2.4 milliamp hours, versus the charge you consume during the active periods is about 0.28 milliamp hours. So you can see that most of your battery life is going into the idle dissipation rather than the active, and so that's where you really want to optimize much more so. And this gives you a nominal battery life of the system of about 3 years. If your system is one where you can actually architect it, where you know the active periods in advance when they're going to occur, then you can one option is for you to put the gauge into shutdown during the idle periods. And then right before an active period is going to start, you can wake the gauge up. It can take OCV readings. It can get an estimate of where the RSOC is. You can keep it powered during the active period, and Coulomb count all the current that has been dissipated during the activity. And then afterward, you can put the gauge back into shutdown when your activity period is complete. So if you're using an impedance track gauge, then you can get a very good, accurate calculation of the RSOC, especially if you wake it up while the battery is still relatively relaxed, and you get a fairly good, accurate voltage measurement there. And for example, if you use a system like this, using the BQ34Z100G1, this lets you reduce your idle current on the order of 30 microamps or so, which basically increase your battery life of your system from 3 years up to on the order of 4.2 years, so fairly significant. Now another approach is if you have a system where the activity periods are not really predictable or can be scheduled, you can actually leave the gauge running, but you can instead go in and modify some of the parameters that control how often it wakes up to measure voltage and current while in sleep mode. These are set in DF settings. Defaults are typically on the order of 5, 10, 20 seconds or so, but these can be programmed up to 255 seconds. And so then you can save considerable power if you take it from defaults. For example, with the BQ40Z50R2, if you change the defaults up to the maximum 255 seconds, you end up saving approximately 30 microamps. However, this means that if you have a load kick on in the middle, if you don't have the wake comparator running, then you would not even notice that until the next 255 second window is completed, and then you wake up. So in general, if you don't know when the load actually kicks on and can wake the gauge, it would be best to have the wake comparator enabled in this mode. And so again, cranking through the calculations on that also extends your battery life from the original 3 years up to a little over 4 years. Next, I'm going to talk about how to use some of the specialized charging algorithms we have in our parts in order to extend the life of the battery packs farther. While many customers are using CCCV style charging, you can also use some of the other charging algorithms we have in our parts in order to give your batteries longer life in system. For example, one of those is using the JADA functionality that we have. Most people are familiar with JADA from the standpoint of trying to ensure safety of the battery packs, but you can also use JADA charging in order to extend your life of the battery pack a little farther. So, we all know that one thing that causes a battery to degrade faster is to have it sitting at high voltage and at high temperature for extended periods of time. And what you find in many systems is a big chunk of the time it's at high temperature is just when it's in the charging process. And so if you go in and kind of think about that and optimize, the regions that you're using for JADA, this is a snapshot from our BQ40Z50R2. So you've got basically 5 active temperature regions and 3 active voltage regions in here besides pre-charge and the kind of excluded regions, where you can specify, distinct charging voltage and charging currents that can be used here. And these can also be, rather than triggered off voltage thresholds, they can also be triggered off RSOC thresholds. And so what you can do is you can try to set these up such that if you get to a point to where, say you're at low voltage and you want to charge fast, so okay, you allow, you're at lower temperature, and so you allow a lot of charging, that starts heating things up and it moves you into higher temperature ranges. If you start getting into higher temperature ranges, then you can start relaxing back on your charging voltage, charging current settings such that as you continue charging, you don't generate quite so much heat, and so you slow down the rate of charging some, but then it reduces the heat that you're generating, and so you kind of tend to be pushed back over into these regions when you're actually charging the battery. So if you optimize these, then based on your use condition, you can then reduce the amount of time the battery sits at, how much heat it generates during charging, and how much time it sits there at that high temperature while it's at a high voltage or a high RSOC level. You can also use some of the algorithms that we've got to modify the charging parameters based on cell degradation over time. For example, the BQ40Z50R2 includes some techniques that can dynamically adjust charging voltage and charging current based on degradation of the cell. That can key off just cycle count It can also just key off the state of health measurements that are taking. And these are permanent reductions, so as you get higher and higher cycle counts, then it will cut back on the charging voltage and charging current and walk those downward, and they're not recovered back to upper levels, to higher levels. We've also got a technique for avoiding cell swelling. So basically it's looking at when do you have a cell at high voltage, and high temperature for an extended length of time. And so if you end up with elevated temperature, high voltage, and over a long period of time, then it will go in and reduce the charging voltage in order to kind of reduce the amount of heat that's being generated from the charging. This one is not a permanent reduction in the charging voltage. This will maintain as long as you're in charge mode, and then as soon as you exit charge mode, then the settings for the charging voltage will reset back to the original levels. Another algorithm that we have that I'm going to talk about is our end of service determination. And this is focused on specifically rarely discharged applications. These are like backup systems where you have batteries that may sit fully charged for months or years without actually having any discharge until suddenly they're used when there's an emergency. The challenge here is, how do you know that the battery is still good, it still has enough health and capacity to supply the backup that's required by the system? Or should it have really been replaced at some point earlier before this backup occurred? Conventionally, this is done by running a maintenance cycle on it. So this is usually done by taking the system offline and then discharging some significant portion of the capacity of the battery and then recharging again to do a maintenance or learning cycle here. So if you do this by taking the system offline, you have to have a spare backup system to keep the system backed up during that time, or you're going to accept the fact that I have less guaranteed backup while I'm doing this maintenance cycle than I would other times. And so if I was in the middle of a maintenance cycle and right then I had an emergency, I would have much lower capacity available for servicing the emergency than I would otherwise. And so what we've actually developed is a new algorithm called end of service determination, which we've rolled into a few of our newer parts here. And this lets us evaluate the health of the battery by only doing very small learning pulses that only discharge the battery, a very small amount, and can keep the system completely online while it's functioning. We run these learning pulses. We basically turn a controlled discharge on the order of somewhere in the C over 100 to C over 10 kind of level. We're triggering that for just a few minutes just to evaluate the transient of the battery. So, for example, we'll have the battery charged. We'll monitor for relaxation. We'll turn on this controlled discharge. This will be a very small discharge, discharging on the order of 1 or 2%. Let it relax again, and then we can trigger and charge back. And what's happening here is the gauge is monitoring the voltage, current, and temperature all through this learning pulse that's being triggered on it, and it's using that to calculate an effective resistance of the cell. So what we're looking for with that resistance is we're expecting a normal cell as it ages to have a resistance profile, something kind of like this, where you end up with some slow increase in resistance until you get severely degraded, and then the resistance starts increasing at a fairly quick rate, and so you end up with this hockey stick type of profile. And you can kind of see some examples, of data that we've taken where, we started out with around 2300 milliamp hour capacity, and then over time it degraded down with multiple cycles down to a little under 1500, so about 35% reduction. And you can see the effective cell resistance that we've measured using this algorithm, where it started out on the order of, say, 115 milliohms, and as the cells degraded, it's increased up to on the order of 220 milliohms. And so this lets us then determine what is the health of the battery, and then we have programmable thresholds in the part, and where we can generate alerts and warnings back to the host system to alert them as to that, hey, we're nearing the end of the usable service of the battery. You should consider replacing the battery pretty soon. Now I want to talk a little bit about some of the battery gauges that we've got, that we've got in production for the high cell count packs. these include three different families here. The BQ78350R1 is paired together with our family of 769, 20, 30, or 40 analog front-end monitor and protector devices. So this allows gauging support up to 15S and also integrates cell balancing and primary protection. We've got the BQ34Z100G1. This is an impedance track gauge only that looks at top of stack voltage and then can back calculate the state of charge, state of health of the pack. And this is applicable to really arbitrarily high voltage systems because it's using a resistive divide down from top of stack. We have customers using this with extremely high voltage systems. It integrates I2C or single wire HDQ communication, also includes LED support. And then we've got the BQ34110, which also has a similar top of stack type gauging for arbitrarily high voltage systems, but this one, rather than using impedance track, is using a CDV gauge. And then it also includes our end of service determination function, which I was just describing for the rarely discharged systems. It's I2C communication with multiple interrupts that are configurable back to a host processor. So you can see a little simplified block diagram of the BQ78350R1 with our 769, 20, 30, or 40. These allow gauging, the 920 up to 5S, the 930 up to 10S, or the 940 up to 15S battery packs. Lithium-ion iron phosphate systems. This includes, it's using CDV gauging, supports configurations up to 320 amp hour, 320 amps of current, includes, thermistor support for monitoring battery voltage. It's I2C communication between the 769X0 and the 78350, and then SM bus over to the system. It also includes SHA-1 authentication and can drive a 5-segment LED or an LCD display. And we can also support through the 769X0 either low side protection FETs or with the 76200 high side charge pump protection. So a little bit more detailed system diagram. You can kind of see how the parts talk I2C over to the analog front end. We've got individual cell taps here, so that allows cell balancing and individual cell monitoring, and then all the gauging is done in the 78350 and provided back to the host over the SM bus connection. The 34Z100G1 is a gauge-only device with algorithm support for lithium-ion, iron phosphate, as well as lead-acid, nickel metal hydride, and NiCad batteries. This is using our impedance track technology. Natively supports up to 65 volts, and then can be, as I mentioned earlier, can be scaled for even higher voltages. Capacities up to 29 amp hours, currents up to 32 amps, which can both be scaled for higher voltage systems. Supports 2-wire I2C as well as the HDQ single-wire communication. We can support up to 4 LEDs directly on the part, and also have support for a port expander for even larger, higher number of LEDs. And SHA-1 HMAC authentication support. And you can kind of see the way this is configured here. We've got multi-cell configuration here. We take top of stack, and we've got a circuit over here, basically kind of like a simplified LDO, generating the power to the gauge, and then we have a resistive divider that's switched on and off by the pack whenever it wants to measure the voltage, and so that prevents the current from flowing through the divider continuously. I2C or HDQ communication, and an alert interrupt back to the host processor. And then the BQ34110 also supports lithium as well as nickel based chemistries and lead acid. This is using CDV gauging. It's very similar to the 34Z100G1 in the voltages it can handle, supporting 29 amp hour and 32 amp current levels. It also includes our end of service determination module for the rarely discharged systems. It includes a separate Coulomb count output that can be configured and set for various thresholds to generate interrupts as you pass certain thresholds of charge that have been either charged or discharged in or out of the battery. And our watt-hour charge termination algorithm, which is maintaining a target capacity while extending the battery life as much as possible. And you can see this configuration for multi-cell, very similar to the 34Z100 in that powered by a separate little circuit here through the power of the gauge, and then the switch divider dropping the voltage down into the back pin. And then we also, for the rarely discharged, are controlling a learning load directly from the part, which in this case is just simply a FET switching in or out a dummy load resistor in the system. So in conclusion, our gauges have a variety of algorithms which can be used and can be used maybe a little differently than they were originally intended to gain some advantages in industrial applications. For large systems, you can do various types of scaling in order to handle higher levels of voltage, large currents, and extreme capacities. We've got ways that we can optimize the power dissipation for heavily duty cycled applications. You can use several of the algorithms that we've got in here to extend the battery life of your packs. And then we've got some specialized algorithms specifically for things like rarely discharged applications, which really are optimized to allow you to get information about the gauge without having to take the system offline. And at that point, I thank you very much for listening. I appreciate your attention. And if you have any more questions, please feel free to visit us at ti.com or our E2E forums, where you can ask questions if you need some clarification on anything. Thank you very much.